Hey, I'm Jack, and a few months ago I was watching NotAnEngineer's Patreon update where he asked for some help on an electronic lead screw project. I'm a software engineer in my day job, so I'd like to think I could program my way out of a paper bag. So I offered my help. It seemed like a nice little project I could do in my spare time. Anyway, I got a test rig, but that's not exactly the same as running it on the real thing. So let's hook it up. For my machine, I chose a NEMA 34 closed loop stepper, since it was the biggest motor I could buy. I know next to nothing about these things, so a bigger motor has to be better, right? So after giving my lathe a quick clean, I found that it didn't have the same hole that NotAnEngineer's lathe had. I mean, it did, but it was just covered up by a potentially extremely important part of the casting. So after cutting that away, with everyone's favorite metal cutting tool, the the angle grinder, I had not only made enough space for the motor, but I'd also undone all the cleaning that I did earlier. Now, out for a challenge, and definitely not being a cheapskate, I chose not to buy any materials for this project. So I made my motor mount out of this piece of angle iron. A little bit of cutting, a little bit of drilling, and a lot of milling later. I had something that fit on my lathe. With some 3D printed pulleys, amazing for prototyping by the way, I could add this belt tensioner by drilling a hole randomly in my motor mount. I just 3D printed the encoder mount because I'm lazy. So with all of that mechanical stuff done, we can finally talk about the software. Automating anything is like an investment in your time. You spend a bunch of it up front with the hopes that it saves you time later. Now this project is more like spending time up front, then spending more time debugging it, then spending more time supporting it in the long run. So I'm not really saving any time here, which is just, I guess, the fate of most projects anyway. Now I'll just gloss over how things work instead of showing you the nitty-gritty most of the time, so you don't actually need to know programming to get this bit. I could make a video about the actual code if people are interested. Leave a comment if you want to roast my code in real time. So after I got the code from NotAnEngineer, I figured out what pieces spaghettified together and put them in their own files. This just means that my monkey brain can focus on one thing at a time. And if I want to add a new button, go to the button file. On top of this, it makes a pretty graph. Along the way, I made a couple of improvements, like replacing the software decoding that NotAnEngineer was doing using interrupts with the hardware decoder that comes built in with the teensy. So now we can decode the encoder without having to encode the code to decode the encoder. On top of that, having less code to support is always a good thing. Secondly, the Breakneck algorithm sent all the pulses with a CPU delay between them. I mean, this is fine, but I'd rather not have the CPU waiting around doing nothing. So I swapped all this run around in a loop, sending pulses to a timer that does exactly the same logic, but doesn't block the CPU. This frees it up to do the math that we've taught these thinking rocks to crave. With that out of the way, let's focus on improving things by making things more complicated. Now, NotAnEngineer was talking about how his motor wasn't up to the task of threading at breakneck speeds. So let's see if we can fix that. Since we've broken up the code, we know we have to focus on what controls the motor, namely the lead screw and spindle files. This application is mainly for threading, but there's nothing saying that we can't apply it to power feed too. So if we're threading up to a shoulder using our electronic lead screw, we'll have an abrupt stop in the gutter. This inertia has to all be absorbed by the motor. If we run through this one more time, but graph it out, we can see that this abrupt stop has the motor trying to decelerate at an infinite rate. Imagine stopping at an infinite rate in a car. What would that do to you? We have to spread this out over some time so we don't mess things up. Can you imagine that I got into this hobby to get away from programming? No? Just me? Anyway, keeping things simple, we can break down our problem into 3 parts. How fast can we start? How fast can we change our speed? And how long, in distance, will it take to stop? Starting from a standstill, we can cheat a little bit, since we know that the motor can go from 0 to some velocity in 1 step. Now this is called the jerk, and I'm using the simplified definition here, because jerk is actually the change in acceleration over time, just like how acceleration is the change in velocity over time. So we've got to jerk our nut to screw our shaft. How do we change the speed of the screw? Can we make it so we don't nut too early? If we just control the spacing between the motor pulses, we can change the speed of the screw. The acceleration is just how much the delay between pulses changes per second. Easy peasy. And that brings us to the bit where I suffered the most. I'm sorry, but we're going to have to sell our souls and do some algebra. Hey, I promised you no understanding of code, not maths. The easy explanation is that we have to calculate how long in distance it would take to get back to the jerk velocity and be able to safely stop the lead screw instantly. This does not translate into mathematics easily though, and so I'll walk us through it. If you want to find the distance to stop, we just need to find the area under this graph, which is easy enough. Unfortunately, we have to solve for x in this case. I know, flashbacks to high school maths, right? My brain is already fried enough as it is. Please don't make me do math. So why do this? Why make us suffer? Well, if we can figure out how long it would take us to stop, we can know exactly when to start decelerating to stop at our thread gutter. So that's it, the final piece of the puzzle. We can now fine-tune our lead screw to start and stop at breakneck speeds and always stop exactly at the shoulder without breaking my lathe. So after all that pain, much of which was off camera, let's see the fruit of our labor. I think I overshot that a little bit. And that makes it all worth it. If you like seeing me suffer and want to see more, think about subscribing. Okay, so I know that you guys are going to have some questions, so I'll try and head some off and answer some now before you write them down in the comments. But if you do want to write them down anyway, that's great. Engagement, right? So, number one, why not make it all CNC? It's not exactly super fun. I mean, having this kind of project is kind of what makes life worth living, right? I just wanted to have a challenge, and it seems like something that would be fun to do. So why not use PID for positioning? Well, I mean, given that I write CRUD apps in my day job, I haven't written C++ in about 10 years, and I don't do motion control, I think I did pretty good. I mean, I'm sure you guys could do better, but that's why it's open source, right? You can go and help out in the GitHub repo, see if you can improve on what I've done. And why use floating point? Well, the thing is, the floating point is only used for the ratio of how much the lead screw should turn in proportion to the actual chuck, the spindle. I didn't want to have it as numerator and denominator because that made actually defining the ratios kind of complicated. And even though it was implied in NotAnEngineer's video, the Breslin algorithm is still in there, so we don't actually get any cumulative losses. So I think that it was a good enough compromise. And on top of that, the Teensy has hardware for it, so like we're not exactly leaving performance on the table. So I think it's fine. Anyway, thanks to NotAnEngineer for letting me help out on this project. Thanks to my lathe for not killing me for giving it a lobotomy. And thanks to you for watching. I hope to see you next time. Look at this cat. Look at that drool. Wow.